Right, this video talks about solving systems of equations using augmented matrices. So let's just jump to an example. So solving systems of equations, linear equations with augmented matrices. So let's look at an example. So let's say you have the system x minus y equals 3, negative 2x minus 3y equals 4. Well, let's look at the constants, the coefficients here. What's being multiplied by the x in the first equation? What constant is being multiplied by the x? It's a 1, right? And what's being multiplied by the y? It's negative 1. Okay. And so you can put these constants into a matrix. So these coefficients, the 1, negative 1, and the 3, negative 2, the negative y, and the 4, can go into a matrix. Let me see if I can make this thinner. You can convert the whole system into an augmented matrix. And so what you do is you just put the numbers into a box, into this matrix. So I have a 1 and the minus 1 and the 3, and then the minus 2 and the minus 3 and the 4. And that's my augmented matrix. Right? It's a matrix with 2 rows and 3 columns. Now when you have a matrix, right, a matrix isn't always referring to a system of equations. I mean, a matrix is just a bunch of, it's a rectangular array of numbers, right? But in this context, we actually have a system of equations that we're trying to solve. And so because of that, the numbers, these numbers on the left side of the equation play a different role than the 3 and the 4, right? These numbers, the 1, the minus 1, the minus 2, and the minus 3, are actually coefficients. And so for an augmented matrix, one thing that I think is really helpful is to just put a line like that down to separate the coefficient part. It's like, here's the coefficient part from the 3 and the 4, which is I don't think there's a good name for this. I mean, sometimes people call this I forgot the name. But anyway, it's this, the point is that you want to keep these two things separate. Okay. And of course, what you can do, so for instance, what you would do to this system of equations on the left, you can match up with the right. So if you have something on the left, okay, I guess we can multiply the first equation by what? How about 2? So 2 times equation 1, and then you add it to equation 2. And what you'll get, well, the first equation will stay the same, x minus y is 3. And, okay, if you do 2 times equation 1, you get 2x minus 2x, 2x minus 2y is 6. And so if you add it, you're going to get, the 2x's will cancel, and then you're going to get a negative 5y equals 10. And similarly, you can just do the same thing here. You could do 2 times row 1. So equation 1 corresponds to row 1, and then plus row 2. instead of equation 2. And if you do that, you're going to get 1, negative 1, 3, and then you're going to get a 0 here, a negative 5, and a negative 10. And notice that, right, these equations match up perfectly. Oops. So what's the next step? Well, we can solve for y. You would divide equation 2 by negative 5. That will give you x minus y equals 3, y equals negative 2. And similarly, that would correspond to... But basically, you just change the word equation to row, right? So you would divide row 2 by negative 5, and you're going to get 1, negative 1, 3, 0, 1. Oh, wait, I messed up. This should be a positive 10. So you get negative 2 here. And now what do? I could substitute y equals negative 2 into the y in the first equation. And one way to do that in terms of adding equations is you can change. So I'm going to do equation 1 turns into equation 1 plus equation 2. In other words, I'm going to replace the first equation by equation 1 plus equation 2. And if I do that, I'm going to get x equals what? What am I going to get? X equals 1. Right? And then I'm still going to get y equals negative 2 at the bottom. And that corresponds in terms of the augmented matrix, I'm going to turn row 1 is going to turn into row 1 plus row 2. And so row 2 stays the same. And row 1 gives me 1, 0, 1. Now how do I read? Well, see, here it's just telling me this. That's the solution. Now how do I read that from the augmented matrix? Well, this is going to turn into... So how do I read out this part? This matrix. I read it. I have to write out the equations. And what I do is these coefficients get multiplied by the variables, and then this bar here, right, that would correspond to an equal sign. So this first equation is going to say 1x1, or okay, 1x plus 0y equals 1, and then the second equation is 0x plus 1y equals negative 2. And of course, that's just the same. The first equation just says x is 1, and the second equation just says y is negative 2. Okay. So I get the same answer here. So anything you could have done with equations by writing it all out on the left, you can do using matrices on the right. Okay. So let's just do a simple example to practice going back and forth between these systems of equations and the augmented matrices. So let's just do an example. Convert the augmented matrix to the equivalent linear system. So 4, 2, negative 1, 2, negative 1, 0, 5, 7. Well, when I see this, so it says this matrix is an augmented matrix, right? And so what's going on is you actually have a bar here. And so how many variables do you have? You actually have 3 variables. You don't have 4 variables. You have 3 variables. And how can... The problem doesn't tell you what the variables are called. So you can just give it any name you want. So you can call these variables x, y, and z, but, you know, if you have a bunch of variables, you can't really use x, y, and z. You have to use subscripts. So let's just use x1, x2, and x3. So this would tell me 4x1 plus 2x2 minus x3 equals 2, negative x1 plus 0x2. Well, if it's 0x2, that's just 0. And then plus 5x3 is 7. So that's my system. That's the system that's represented by this matrix. And so it is important, you know, to keep in mind that there is this vertical bar. I mean, the vertical bar isn't part of a matrix. And so that's why in a bunch of books they don't actually write down the bar, because that's not part of a matrix. But I think it's a good idea to kind of include it when you're trying to learn the subject, because basically what will happen is not only this matrix is relevant when we're talking about general kind of linear algebra, but also this coefficient matrix, this part, is also important. Oops. But here in this context, right, this matrix, let's call this matrix A. So this is the coefficient matrix, right? This matrix, we don't think of it as an augmented matrix, okay? Because this matrix just has the coefficients in the linear system, right? These are the coefficients that are being multiplied by the variables. And then this other part, this part, we usually think of it as a vector 2, 7. And then this is usually B. And so this system, this augmented matrix, and then this is something that we'll see when we talk about matrices times vectors. We're going to learn how to multiply a matrix by a vector. The augmented matrix and the system of equations, right? This system of equations that we just wrote, corresponds to the matrix vector equation AX equals B. So basically, whenever you have a system of linear equations like this, you can always rephrase it as an equation where you have this coefficient matrix and then you have the vector B, which corresponds to these constants on the right, and then that's the thing that we're trying to solve. So trying to solve, and then this x will be a vector, b is a vector, so we're trying to solve for all the different vectors x, such that when you do the matrix A times the vector x, you get the vector B.